Dear learners, I am Gaurav Kumar Agrawal, Assistant Professor at the University Teaching Department, CSPTU Bhilai. In today's session, we are advancing to the topic of foundation bearing capacity. We will delve into the critical aspects of the bearing capacity, which is a fundamental concept in geotechnical engineering. Understanding bearing capacity is essential for ensuring that a foundation can safely support the loads imposed by the structure without experiencing any type of failure. We will explore different factors that influence bearing capacity, including soil type, foundation depth, and the load distribution. By the end of this session, you will be equipped with the knowledge to assess and design foundations with adequate bearing capacity, thereby ensuring the safety and stability of the construction projects. We will discuss the key points. First, essential conditions for the foundation design. Second, definitions related to the bearing capacity. Third, methods for estimating bearing capacity. Fourth, settlement of foundations. Fifth, methods for enhancing safe bearing capacity of soils. Sixth, causes of foundation failures and their remedial measures. So, first is essential conditions for the foundation design. To ensure a foundation is properly designed, it must meet two critical criteria. First is safety against ultimate failure. The foundation must have a specified safety margin to prevent catastrophic failure. Second is controlled settlements. The settlements under working loads should remain within allowable limits to support the superstructure effectively. The dimensions of foundations are determined based on the soil's bearing capacity, which is assessed considering these two essential conditions. The term bearing capacity refers to the soil's or rock's ability to support the loads. What are the various definitions related to the bearing capacity? First is gross pressure intensity, denoted by the Q. This is the total pressure at the footing space, accounting for the superstructure's weight, the footing self weight, and any type of earthfall. Second is net pressure intensity, denoted by the Qn. This is the additional pressure or the difference between the gross pressure after construction and the original overburden pressure. It is calculated by Qn is equal to Q minus gamma d, where gamma is the unit weight of the soil above the footing level and d is the depth of the footing. Then the ultimate bearing capacity, denoted by the Qf. This is the minimum gross pressure intensity at the foundation base that causes shear failure of the soil. Then the net ultimate bearing capacity, denoted by the Qnf. This is the minimum net pressure intensity that results in soil shear failure. The relationship between ultimate and net ultimate bearing capacities is Qf is equal to Qnf plus gamma d. Then the net safe bearing capacity, denoted by the Qns. This is the net ultimate bearing capacity divided by a safety factor f. So, Qns is equal to Qnf divided by f. Next is safe bearing capacity, denoted by Qs. This is the maximum pressure that the soil can safely carry without experiencing any risk of shear failure. It is the sum of the net safe bearing capacity and the original overburden pressure. The equation is Qs is equal to Qns plus gamma d and is equal to Qnf divided by f plus gamma d. Sometimes it is also described as the ultimate bearing capacity divided by the factor safety f. Then the allowable bearing capacity pressure, denoted by Qa. This is the net loading intensity at which neither soil shear failure nor excessive settlement occurs. It depends on the subsoil conditions and the type of structure and is generally less than the safe bearing capacity. Then the next is various type of methods for estimating bearing capacity. The bearing capacity of soil can be determined using the following methods. First is analytical methods. It involves soil parameters. Second is plate load test, conducted directly on the soil. third is penetration test, and the fourth is presumptive bearing capacity values. These are provided by the various type of codes. So, first is analytical methods. Several analytical techniques have been developed to estimate the ultimate bearing capacity of the soil. These methods rely on two crucial shear parameters of the soil. First is angle of internal friction denoted by phi, second is cohesion denoted by C. The angle of internal friction and the cohesion are typically determined in a laboratory setting by performing shear test on soil samples. These samples are ideally undisturbed and collected from boreholes or test pits to ensure accuracy. Among the various theories that have been proposed for calculating soil bearing capacities, two notable ones are: first is Rankine's analysis, second is Terjaghi's analysis. So, first is Rankine's analysis. As the load on the footing increases and the approaches the ultimate bearing capacity QF, the soil beneath the footing reaches a state of plastic equilibrium. This equilibrium condition is critical in determining the bearing capacity of the soil under the foundation. Rankine's formula for ultimate bearing capacity QF of cohesionless soil is given by the equation QF is equal to gamma d 1 plus sin phi divided by 1 minus sin phi ka whole square, where gamma is the unit weight of the soil, d is the depth of the footing, phi is the angle of internal friction. The next theory is Terjaghi's analysis. Terjaghi's analysis addresses the condition of complete bearing capacity failure, typically known as general shear failure. This analysis assumes that the soil behaves as an ideally plastic material. According to Terjaghi's theory, when the load on a shallow footing where the depth d is equal to or less than the width of the footing increases, the loaded soil fails along a composite surface denoted as ABC B1 A1 as shown in the figure. In Terjaghi's model, the failure mechanism involves the development of a slip surface that forms a composite shape, indicating the zones where the soil experiences plastic yielding and ultimately fails. This conceptual model helps in understanding and predicting the bearing capacity of the soil under different loading conditions. Terjaghi gave the following two important equations. First is QF is equal to CNC plus gamma dNq plus 0.5 gamma b n gamma, or it can also be written as QS is equal to 1 divided by F in the bracket C plus NC plus gamma d multiplied by NQ minus 1 plus 0.5 gamma b n gamma bracket closed plus gamma d, where NC, NQ and n gamma are the dimensionless numbers called the bearing capacity factors, the value of which can be obtained from the table shown. We can see in the table the various Terjaghi's bearing capacity factors. Then the next theory is plate load test. The plate load test is conducted in the field to assess the ultimate bearing capacity of the soil and to predict potential settlement under specific loading conditions. This test involves placing a rigid plate, typically made of steel, at the foundation level and applying incremental loads while recording the resulting settlements. During the test, the plate is loaded in increments and the corresponding settlements are measured. The ultimate bearing capacity is identified as the load level at which the plate begins to sink rapidly. This method operates under the assumption that the soil strata down to the depth where stresses are significant are relatively uniform. So, what are the various specifications of the plate and the test setup? The bearing plate used in the plate load test is square in shape with a recommended minimum size of 30 centimeter and the maximum size of 75 centimeter. The plate is machined on all the four sides and edges to ensure accuracy, and it must be thick enough to resist any bending stresses from the maximum expected load. The thickness of the steel plate should be at least 25 mm. Then the test pit preparation. The width of the test pit should be 5 times the width of the plate BP. A small square hole equal in size to the plate is dug at the center of the pit. The bottom of this hole should be at the same level as the actual foundation. The depth dP of the hole is determined by the ratio dP by BP is equal to foundation depth by foundation. The next is loading conditions. The test plate is loaded using a hydraulic jack. The reaction force of the hydraulic jack can be managed by either of the two following methods. First is gravity loading platform method. A platform is built over a vertical column resting on the ground. The load is applied using sandbags, stones or concrete blocks. Then the next is reaction truss method. In the gravity loading method, the general arrangement involves constructing a platform and loading it with weights. As the load is applied to the test plate, it settles. Sensitive dial gauges are used to measure the settlement of the plate. For a square plate, 2 dial gauges are typically employed, mounted on an independently supported datum bar. As the plate settles, the ram of the dial gauges move down and the settlement is recorded. The hydraulic jack's load gauge indicates the load applied. Then the bearing capacity based on the settlement. While the safe bearing capacity determined from the shear failure is important, the settlement of the footing also influences the soil's bearing capacity. This can be obtained from the load settlement curve corresponding to the desired settlement of the test plate. Permissible settlements of the footings are generally specified in the building codes, and the corresponding settlement of the test plate can be calculated using specific relations for different type of soils. Settlement in granular soils can be calculated by the equation Rp is equal to 4 by 3 Rf multiplied by Bp in the bracket B plus 0.3 divided by B in the bracket Bp plus 0.3 whole square, where Rp is equal to settlement of plate of width Bp and Rf is equal to permissible settlement of actual footing of width B. For clayless type of soils, the following relation may be used: Rp is equal to Rf multiplied by Bp by B. The safe bearing capacity is then lesser of the following two values: safe bearing capacity found on the basis of shear failure and net loading intensity corresponding to settlement Rp of the plate. Then the next is limitations of the plate load test. The plate load test has several limitations. First is depth of the soil influence. The test results only reflect the soil properties within a depth less than twice the width of the bearing plate, which corresponds to a pressure bulb of 1/10 of the loading intensity at the test plate. Since the actual foundations are typically larger, the settlement and the shear resistance depend on the properties of a much thicker soil layer. Then the duration of the test. The plate load test is a short duration test and does not provide the ultimate settlement, especially in the cohesive soils where long term settlement can be significant. Then the foundation size test. The test is influenced by the size of the foundation. In clayless soils, the ultimate pressure for a large foundation is similar to that for the test plate. However, in dense sandy soils, the bearing capacity increases with the foundation size, leading to conservative values when using smaller test plates. Then the next test is penetration test. First, we will see the overview of the penetration test. Penetration test measure the resistance encountered by a sampling device such as spoon, cone or other tools under either dynamic or static loading conditions. The resistance is empirically related to various engineering properties of the soil such as its density index and the bearing capacity. Two widely used penetration tests are: first is standard penetration test, which is in short known as SPT test. Second is Dutch cone test. Now first we will be studying about the standard penetration test. The standard penetration test, as specified in IS 2131 published in 1981, is conducted in a clean bore well with a diameter ranging from 55 to 150 mm. The side of the hole may be supported using casing or drilling mud. A thick walled split tube sampler with an outer diameter of 50.8 mm and an inner diameter of 35 mm is driven into an undisturbed soil at the bottom of the hole. The sampler is then driven by a 65 kg drive weight with a free fall of 75 cm. The sampler should have a minimum open length of 60 cm. Initially, the sampler is driven through 15 cm as a sitting drive. It is then driven an additional 30 cm and the number of blows required to achieve this penetration is recorded. This count of blows is known as the penetration resistance, denoted by the N. In cases of very fine or silty saturated sand, there may be an apparent increase in resistance. Terjagi and Peck recommended using an equivalent penetration value denoted by Ne instead of the observed value of the N. When N exceeds 15, Ne is calculated using the equation Ne is equal to 15 plus half multiplied by N minus 15. Then the next is Dutch cone test. The Dutch cone test is employed to obtain a continuous record of the soil resistance by steadily penetrating a cone under static pressure. The cone has a base area of 10 cm square with a diameter of 3.5 cm and a vertex angle of 60 degree. The cone is mounted at the end of a steel driving rod, which is guided through a steel tube known as the mantle with an external diameter matching the cone's base. The cone can be driven into the soil either by itself or together with the tube using a jack. Initially, the cone alone is penetrated to a depth of 8 cm and the maximum resistance encountered is recorded. Following this, the steel tube is pushed down to the cone and both the cone and the tube are driven further into the soil to a total depth of 20 cm. This measurement includes both the cone resistance and the frictional resistance along the tube. The Dutch cone is particularly valuable for assessing the bearing capacity of the soil, especially in cohesionless soils like fine sands with varying densities. The cone resistance, denoted by QC, and its unit is kg per centimeter square, is typically 5 to 10 times the penetration resistance N. Then the next topic is settlement of foundations. Settlement refers to the vertical downward movement of a structure's base. Its impact on the structure depend on several factors, including the amount of settlement, its uniformity, the duration over which it occurs, and the nature of the structure itself. Foundation settlement can be attributed to one or more of the following causes. First is elastic compression. The foundation and the underlying soil may experience elastic compression when subjected to loads. The next is inelastic or plastic compression. This type of compression, which is significantly larger than the elastic compression, occurs in the underlying soil and can be predicted using consolidation theory. Groundwater lowering. Fluctuations in groundwater levels, particularly in loose granular soil, can lead to soil compaction and ground surface settlement. In fine-grained soils, lowering the water table causes consolidation settlement. For instance, the city of Mexico has experienced significant settlement due to the groundwater lowering, earning it the nickname Sinking City of Mexico. Then the next is vibrations. Activities such as pile driving, blasting, and operating oscillating machinery can cause settlement in granular soil deposits. Then the next is seasonal changes. Expensive clays may swell or shrink with seasonal moisture variations, contributing to the settlement. Then the next is ground movement, surface erosion, slow creep, or landslides on earth's surface or slopes can lead to settlements. Then what are the various implications of the settlement? Some degree of elastic and inelastic settlement is inevitable and should be accounted for in the design phase. Uniform settlement across the building area generally causes minimal damage. However, differential or uneven settlement can induce stresses within the structure. For example, in brick structures, this might lead to numerous cracks at the joints, whereas more rigid structures could experience overstressing of the certain members. It is recommended that the allowable pressure be chosen to ensure that the maximum settlement of any individual foundation does not exceed 2.5 cm. For uniformly loaded continuous foundations and spread foundations of similar size, the differential settlement is typically no more than half of the maximum settlement. Normal structures such as office building or residential flats can generally accommodate differential settlements up to 18 mm between columns placed at 6 to 8 meters apart. According to National Building Code of India, which is SP 7/2005, differential settlement must be limited to a level where the superstructure can be adjusted without significant distortion. Foundations should be designed to ensure that the total settlements are restricted or that special measures are taken to prevent damage to building connections such as drains. For simple spread footings on sandy soils, the allowable bearing pressure should be set up so that the differential settlement does not exceed 1/300 of the footings width, typically achieved by limiting total settlement to 50 mm. For clayless soil, the allowable bearing pressure should be such that the differential settlement does not exceed 1/300 of the footing width, with total settlement generally limited to 75 mm. American courts suggest that if the maximum total settlement is kept within a reasonable limit, differential settlement will be proportionately less, often around 3/4 of this limit, depending on the type of structure and the load distribution. The allowable maximum settlement values for different type of structures are as follows. For the commercial and institutional buildings, 25, for industrial buildings 38 mm, for warehouses 50 mm, and for the special machinery foundation typically less than 0.5 mm. Then what are the various methods for enhancing safe bearing capacity of the soils? When the safe bearing capacity of the soil is insufficient, resulting in excessively large and costly footings, it becomes necessary to improve the soil's bearing capacity. Several techniques can be employed to achieve this enhancement. First is increasing the depth of the foundation. Increasing the depth of foundation can enhance soil's bearing capacity, especially in granular soils, as the overlying material adds confining pressure. However, this method is often not economical due to higher construction cost and increased load requirements. It is most beneficial when a stronger soil layer is encountered at greater depths. Then the next is soil compaction. Soil compaction is a common related method to improve bearing capacity and reduce settlement. Effective compaction can be achieved through various techniques such as ramming moist soil. Moist soil can be compacted using hand rammers, mechanical rammers, or vibratory rollers, which reduces voids and consequently settlement. Rubble compaction, spreading and compacting a 30 to 45 centimeter thick layer of well graded rubble over the foundation level can enhance soil bearing capacity. If the rubble layer gets buried, an additional 15 centimeter thick layer is added and compacted manually. Then flooding the soil. Flooding loose sands increases bearing capacity by compacting the soil, particularly effective for sand dunes. This method has been used successfully to support heavy loads in desert areas. Then the vibration. Heavy vibratory rollers and compactors can improve granular soils up to 3-meter depth. Combining vibrations with flooding can significantly enhance the soil's bearing capacity. Foam vibrators or platform vibrators can be used to cover large areas effectively. Then the vibroflotation. This commercial technique uses a vibrofloat, a vibrating cylinder with a water jet to compact soil while simultaneously adding clean sand. This method is particularly useful for large areas requiring supports for heavy loads. Then the compaction by preloading. This technique accelerates soil consolidation by applying a temporary load before construction. The load is removed prior to the foundation construction, reducing long-term settlements. Then the using sand piles. Hollow pipes driven into the ground at close intervals can compact the surrounding soils. These pipes are removed gradually and the holes are filled and rammed with sand, creating sand piles that improve soil bearing capacity. Then the next is soil drainage. Drainage is crucial for increasing soil bearing capacity, especially in saturated conditions. Excessive water decreases soil shear strength. By reducing the void ratio through drainage, soil bearing capacity can be improved. Then the soil confinement. To prevent settlement due to lateral movement in loose granular soils, confining the soil outside the foundation's perimeter can be effective. This can be achieved by driving seed piles around the foundation area, thereby preventing lateral soil movement. Then the next is grouting. Grouting involves injecting cement or other grout materials into the ground to fill voids, cracks and fissures while strengthening the soil. This technique is beneficial for loose gravels and fractured rock strata. Then the next is chemical treatment. Chemical treatment involves injecting chemical into the soil instead of cement grout. These chemicals solidify and strengthen the soil, enhancing its bearing capacity. Then what are the various causes of foundation failures and its remedial measures? Foundations can fail for various reasons, each requiring specific remedial measures. First cause can be unequal subsoil settlement. Unequal settlement of subsoil is a critical concern in structural engineering as it leads to significant structural issues such as cracks, tilting and even rotation of the building. These issues primarily arise due to variations in the subsoil's property, which may result from the various factors like non-uniform subsoil conditions, unequal load distributions, eccentric loadings. To mitigate the effect of unequal subsoil settlement, the measures that can be employed are design foundations on rigid strata, proper footing design, limit soil pressure and avoid eccentric loading. Then the next cause can be unequal settlement of masonry. Masonry structures between the ground level and the footing can experience unequal settlement leading to cracks in the superstructure. This issue often arises due to shrinkage or compression of the mortar joints. To prevent unequal settlement of masonry, the practices that should be adopted are use strong mortar with thin joints, restrict masonry heights during construction and proper watering of the masonry. Then the next cause is subsoil moisture movement. Changes in the moisture content of the subsoil, particularly in cohesive soils like clays, can cause significant foundation problems. The soil can either shrink or swell depending on the moisture content, leading to vertical movement of the foundation, which can result in cracking. To minimize the impact of subsoil moisture movement, the following precautions can be considered. Special precautions for the expensive soils, proper drainage and moisture control. By implementing these measures, the risk associated with unequal subsoil settlement, masonry settlement, subsoil moisture movement, lateral pressure on walls and lateral movement of subsoil can be significantly reduced, thereby enhancing the overall stability and longevity of the structures. Dear learners, we have reached the end of today's session. I hope you found it informative and engaging. Thank you for your attention. See you in the next class. Thank you.